In this lesson, you will learn about lockdown mode, implementing row-level security for AI apps. Row-level security, RLS for short, is an enterprise security feature in PostgreSQL that alters the database engine's access path. Instead of granting blanket permissions to a table via traditional role-based access control, that is RBAC, RLS forces the database to evaluate custom context-aware security policies on a row-by-row basis. In multi-tenant AI applications, RLS is a critical architectural pattern. It establishes a data isolation sandbox that prevents LLM orchestrators, vector search functions, and chat APIs from accidentally bleeding data across tenant boundaries or prompt injection attacks or context pollution. So let's learn about the mechanics of how the Postgres engine rewrites queries under the hood. When a query is executed against a table with RLS enabled, the PostgreSQL query planner intercepts the incoming statement and transparently modifies it. It appends implicit security filters before generating the final execution plan. For example, say the incoming client query is select star from documents. Now the RLS security engine will change this SQL statement given by the end user and convert it into something like select star from documents where tenant underscore id is equal to current setting app.current tenant id. So the user gives this query, that is select star from the documents table, but the PostgreSQL security engine will convert this user query into this highlighted query. So this conversion will be done internally by the RLS security engine. Now, because this query rewriting happens natively within the optimizer, application developers are completely insulated from this query rewriting. Let's understand the critical performance trap, that is the leak proof functions and the row-level security. While the row-level security provides ironclad security, it can introduce massive query degradation if misunderstood. By default, PostgreSQL will evaluate standard user-defined functions or complex clauses before applying the RLS policy if it thinks doing so speeds up execution. If your RLS policy depends on an expensive user-defined function, or if a user inputs a malicious function designed to leak information via error messages, data can bleed. To prevent this performance and security leak, functions called inside RLS policies must be explicitly marked as leak proof. This forces PostgreSQL to always execute the RLS policy expression first. So the next, let's learn about the comparison between application level tenancy and native database row level security. So as you can see, these are the various vector security model. Then we have the application level filtering where the tenant ID is equal to the user supplied tenant ID. The next talks about the native PostgreSQL row level security. You can go through these and understand by yourself. Let's move ahead and learn about the indexing strategies for high performance row level security. To maintain sub millisecond lookups under high concurrency multi-tenant pressure, your indexing strategy must match your RLS policy structure. In the composite strategy, always create a composite index starting with your security discriminator column. For example, tenant ID, document ID, or tenant ID and the vector embedding column. The reason is this structure allows the query planner to run an index scan that instantly jumps to the isolated partition block for that specific tenant, entirely skipping sequential scans of foreign rows. Now let's discuss about the ultimate nightmare scenario for any modern AI platform architect, that is cross-tenant data leakage. Imagine this. You are building a corporate AI knowledge base assistant. Two of your enterprise clients, let's call them client A and client B, are uploading high security vector embeddings into the exact same database cluster. Client A is processing proprietary internal financials. Client B is storing system prompt workflows. So late at night, an application developer on your team writes a new complex RAG retrieval route. They get tired, they miss a deadline, and they forgot to add where tenant ID is equal to client ID to a single query execution wrapper. Suddenly, an end user from client B asks the chatbot a question, and the app accidentally serves them a consolidated context window containing client A's confidential financial variables. So your platform's reputation is ruined, security protocols are violated, and all because you trusted application code to handle data isolation. So why place that massive security burden on your application layer when PostgreSQL can natively sandbox your data using row-level security? Within the row-level security, even if your API code issues a blanket select star statement, the database engine intercepts the query and explicitly strips out any rows that don't belong to that specific session context. Let's implement this securely on our server. So first, let's look at our core data setup. We have an AI knowledge base table. To protect it, we must explicitly tell PostgreSQL to lock down this table by activating row-level security. Let's do a practical demo. The context and the scenario here is you are the lead security engineer for an enterprise AI chat log application. The system logs high priority vector interactions from multiple enterprise tenants into a central table named tenant underscore embeddings. During a code audit, you notice that junior engineers are writing dynamic application queries that manually inject customer credentials into queries. If the application layer is compromised by an adversarial prompt injection attack, the attacker could manipulate the parameters to scrap vectors from other companies. You need to enforce native database row-level security, implement an optimized composite index strategy to keep lookup times fast, and configure a secure connection state workflow. So the first step is to create a table named tenant underscore embeddings containing a tenant ID tracking variable and a mock vector column. So let's get the SQL statements here, the SQL code. Let me copy this. I execute it in the command line interface. As you can see, I have created the table tenant underscore embeddings. The next task is to enable row level security on this table. So for that, you need to alter the table tenant underscore embedding and enable row level security. So this is the command that you need to execute in the psql CLI to enable the row level security on the table. So okay, so before enabling the row level security, we need to enter some realistic multi-tenant simulation data entries into this table. So copy these SQL statements and paste it here. So as you can see, I have inserted few rows into the tenant underscore embeddings table. Then let's go ahead and enable the row level security. Okay, so as you can see, this is the command to enable row level security in our table tenant underscore embeddings. Alter table name of the table and then enable row level security. So let me enter here. So this is the command that I have given here, and as you can see, it has enabled the row level security in the table that we have created, that is tenant underscore embeddings. So the next task is to construct an isolation policy that relies on a secure runtime session variable, that is app.active underscore tenant. So now we need to architect the isolation security policy. This uses the safe context string reader. The second argument true ensures no error if empty. So this is the command. Let's copy this. Let's go to the CLI and paste it here. As you can see, we have created the policy successfully. The next task, that is the fourth task, is to write a high performance index that eliminates sorting and handles filtering concurrently. So let's see the code. Let's see the SQL statement here. Okay, so let's create a composite index optimizing the exact filter injection step applied by the RLS rewriter. So let me copy this SQL statement here to create the index. So I'm copying these SQL statements. I'll go to the command line editor and I'll paste it here. As you can see, the index has been created successfully on our table tenant underscore embedding. And the next stage is to demonstrate the security sandbox by simulating session switching inside a single transaction runtime. So the test case here is validate security as tenant. So let's give this statement command line interface. Okay, so we have set the active tenant now. Then you can observe the execution layout. So let's give the command to create the execution plan. So this is what is the query plan, as you can see here. Another test case is to validate the security context switching to tenant 808. So let's change the security context to tenant 808. So let me copy this code, paste it here. As you can see, the tenant has been set to 808 now. Selected all the source document and the vector data from the tenant underscore embeddings table. So as you can see, there are 4 rows here. Okay, so moving next, the next test case, that is test case C, is to verify empty or unauthenticated states that are completely blocked. So this is what is the SQL syntax. So let me verify this. Then let me verify the count from the tenant underscore embedding table. Let me just paste this command. So as you can see, so the number of rows are 4. We need to give commit statement as well. So let me, so this is the commit. So as you can see, there is no transaction that's currently in progress. So returns 0 rows safely. So never reference non-indexed or uncached external user-defined tables inside an row-level security using the condition clause, as this forces PostgreSQL to run nested loop scans for every evaluated row. Always ensure your connection manager resets or overrides custom session settings immediately upon transaction entry to prevent connection pollution within pool managers like PG Bouncer.